Hi everyone. So currently we have been discussing about hot consolidation or full density processing. So here, in order to achieve densification, simultaneous application of heat and pressure is the approach. So unlike the conventional sintering process in which the green compact is sintered separately, in this case the compaction and the sintering operations are kind of combined in a single step, right? Because here, as I said, pressure and heat are applied simultaneously, okay? And in the previous class, we were discussing about the mechanisms of this hot consolidation, and what we have seen is that the mechanisms can be derived from the creep deformation mechanisms, because in this case also a similar kind of deformation takes place at high temperature when the compact is pressed at a particular temperature. And if we can account for the porosity which is present in the green compact, the creep equations can be used for the mechanisms which are operative in this hot consolidation process, okay? So from there we have seen that if we could account for the porosity, as I said, the same creep equations can be used for the hot consolidation or the hot pressing mechanism. So here in this table you can see those things, the equations and the corresponding mechanisms. So in case of simple creep where an external stress is applied at a particular temperature, this part that you see over here, this will be only the applied stress sigma A. But now that we are talking about a green compact which is being pressed at high temperature, apart from the stress, we also need to consider the porosity which is present, and that is where this term phi PA has come into picture here, where phi is the stress intensification factor which comes in due to the presence of the pores, and PA is the applied pressure. And apart from that, we have also seen that the pores have a curvature, and due to that there is a stress which is given by this term gamma SB by R, okay? So when you combine these two, you have the effective driving force for the hot consolidation process, right? So that is how the porosity has been taken into consideration in this case when you replace the applied stress with the effective driving force, which takes into account both the applied pressure as well as the presence of the porosity, right? And then finally we have seen a generalized form of the densification rate, which is given by this particular equation. And here the exponents m and n that you see, those can have different values depending on the operative mechanism. Yeah, so again coming back to this mechanisms of the hot consolidation process, this diagram also shows the mechanisms as a model considering spherical particles in contact. So here you can see that at high stresses, when the stress exceeds the yield strength of the material, plastic deformation begins and the densification occurs instantly once the plastic deformation begins, okay? So that's what you see in the first set of pictures. And then when the stresses are low, then the diffusional flow can combine with the applied stress, and the densification occurs by the creep process. And the diffusion can occur either through the lattice or through the grain boundaries. When it occurs through the lattice, the creep process is known as Nabarro-Herring creep, and when it occurs through the grain boundaries, it is known as Coble creep, okay? So this also we have discussed already, right? So depending on the applied stress, it can either densify through the plastic deformation process itself or by a time dependent deformation process, or creep. Okay. Okay, so now that we have understood the mechanisms, let us go ahead and see the different methods which are used for full density processing. So we start with this hot pressing process. So here pressure is applied during the sintering process. So it is basically stress enhanced densification by application of external pressure. And if you talk about the uniaxial hot pressing, it is similar to the die compaction that we have talked about before, except that the die assembly is heated up, right? So that is the only difference. Otherwise, as you can see from here, from this diagram, this is very similar to the die compaction, where you have the die in which the powder is filled, right? And then you have an upper punch and there is a lower punch through which the pressure is applied onto the powder, right? So here, in order to heat the powder, you have this furnace around this die. You can see these heating coils over here. So as the powder is heated up, it is also simultaneously pressed, okay? So the initial compaction in this case again happens by the rearrangement and the plastic flow as the powder is pressed and the temperature is raised. And grain boundary and volume diffusion become dominant in the later stages when the stresses are high and when the compact reaches the sintering temperature and is at a higher temperature. The process is slow and the control over the heating and the cooling rates are not that great, and typical maximum temperature which is used in hot pressing is about 2200 degrees Celsius and the typical pressure is about 50 MPa, okay? And in many cases vacuum is used to minimize the contamination. Contamination of the compact by the die is a major problem, particularly at high temperature, and therefore vacuum is used in most of the cases in order to eliminate the chances of contamination. And this is a process which is widely used for making unique composition and composites, because here the powder can be mixed with some other elements, some other metals to give rise to an alloy. And this alloy composition can be varied depending upon the requirement in the final product. And this is a simple process where it is easy to control the composition, and therefore it also provides you an opportunity for making unique compositions. And you can also mix a second phase which does not dissolve in the metal, and that will give rise to a composite, okay? And since the sintering process is pressure assisted here, the densification of a material like composite where you have insoluble particles can be done easily in this case, okay? We have talked about the cold isostatic pressing before, or the SIP process for compacting the powder by applying the pressure uniformly from all sides. So here the hot isostatic pressing or HIP is the hot counterpart or the hot consolidation counterpart of the SIP process, okay? So like we have seen, the hot pressing or the uniaxial hot pressing is the counterpart of the uniaxial compaction. Here the hot isostatic pressing is the counterpart of the cold isostatic pressing, wherein the compaction occurs at a higher temperature and therefore the compaction and sintering processes are combined into one step, and at the end of the process you get a fully dense compact. So here a gas tight container is used to shape the powder, and in order to do that, glass, steel or tantalum are the commonly used material for the container depending on the maximum temperature. The container is heated, then it is vacuum degassed, and finally sealed before it is actually subjected to the heaping process. If the degassing is not adequate, then it will lead to porosity. So you have seen before that if there are trapped gases in the pores, it limits the final densification and it is difficult to achieve full densification, right? And therefore, here the vacuum degassing which is done has to be done carefully so that there are no chances of trapped gases and you do not end up with porosity in the final sintered compact. So in order to pressurize the powder, in this case, a high pressure gas, a high pressure inert gas like argon or nitrogen is used, and temperatures up to 2200 degrees Celsius and pressure up to 200 MPa can be used for hot isostatic pressing. And after the heap cycle, the container is stripped from the densified compact, and this is a process which is quite attractive for making aerospace alloys, composites and tool steels. Okay, and one variant is to use a densified compact with certain amount of porosity, let's say 8 to 10% of porosity. The compact in that case has been already shaped into the desired final shape, and the remaining pores are closed by the heaping process, right? So here it is just to close the remaining pores which are there in the compact, which is already made into the final shape. And another approach of the process is to create the pressure by volatilization of a liquid, and the pressurization rate in this case is much higher compared to gas pressurization, and the densification occurs by plastic flow instead of creep. So here we have seen that when the stress is high and if it exceeds the yield strength of the compact of the material, then the plastic deformation will begin and the densification will occur by plastic flow. So that is what is going to happen when the pressurization is done by volatilization of a liquid, because here it achieves a higher pressure and therefore the densification occurs by plastic flow instead of creep. Okay, so this is a schematic which shows the setup used for the hot isostatic pressing. So this is the can which is used to fill the powder. That's the first step of the heaping process, and then the powder has to be degassed. So a vacuum chamber is used to degas the powder. So that's the vacuum bake-out process to remove any trapped gases. And finally, once it is degassed, it is transferred to the heaping chamber where it is heated up under isostatic pressing. Okay, and this is the pressure temperature cycle that you can see from here. When the pressure is applied, the temperature also is simultaneously applied, and at the sintering temperature where it is held for a particular period of time, the pressure is also held during that time for the densification to occur. Okay, so this is an example of a heaping cycle for tungsten carbide, which is a material difficult to process by conventional sintering, because this is a very hard material, so it is difficult to densify by conventional sintering processes. So the hot isostatic pressing is quite attractive for this kind of materials which are difficult to process by conventional routes. Okay, so here you can see the loading starts and simultaneously the heating is also done. So as the compact reaches the sintering temperature and held, the pressure is also held, as I said, at a particular value depending on the type of material. And once the sintering is over and the compact is cooled down, the pressure is also released. Okay, so as you could see here on the right hand side part of the diagram. Okay, So this is kind of a temperature pressure cycle which is applied in this case, unlike the conventional sintering process where there is only the heating cycle, right? Let us talk about one more processing technique. This is powder forging. So here it's a high temperature and high strain rate process, and it has less number of steps compared to metal forging, right? So you may know about forging where a metal is heated up to a particular temperature and then it is hammered or deformed to give it a particular shape, and it can also modify the microstructure of the material. So in this process of powder forging, a sintered powder preform with about 10 to 25% porosity can be fully densified in one forging strike, right? So in case of metal forgings, you might have seen the heated metal is struck several times by a hammer-like blow. A typical example of the metal forging process can be seen in a blacksmith shop, where a heated metal is subjected to repeated blows of a hammer to give it a particular shape. But in this case of powder forging, the full densification can be achieved in just one forging strike. Okay. The shape and density of the preform, which is prepared by conventional pressing and sintering, has a huge influence on the densification process. So as you can see from here, first a preform is formed. So this is done by the conventional compaction processes that we have talked about. The powder is pressed in a die and given a particular shape, and then it is sintered to reduce the porosity level, so that when it comes for the powder forging process, the porosity is only about 10 to 25%, as I said before. Okay. So now if this compact having certain amount of porosity like that is subjected to forging operation in the forging die, the densification can be achieved in just one forging strike, as I said. So here is a schematic of the process. Here is the initial preform having a particular amount of porosity, and then it is subjected to the forging operation by loading the compact into a forging die. And as the pressure is applied in the forging die and the compact takes up the shape of the die cavity, the densification also occurs, and finally at the end of the forging operation, 100% or full density is achieved. And one thing that I should mention over here is that a porous compact shows a higher work hardening rate due to the collapsing of the pores and the associated densification which occurs. For example, the strain hardening exponent N for sponge iron can be written in this form as a function of the fractional density F, right? So as the densification is achieved due to the collapsing of the pores, the strain hardening also increases, which you can see from this equation over here, where 0.31 is the value of the strain hardening exponent for fully dense iron. Okay. Now, powder forging is a combination of both densification and flow under a uniaxial stress. As the stress is applied, the pores will collapse, and the pore collapsing is very different from what you have in the heaping process, because in case of the forging operation, the compact is subjected to higher amount of shear. Okay. And because of that, the collapsing of the pore as to how the pores are closed is very different from the heaping operation which we have talked about before. And this is a schematic which shows the collapsing of the pores as to how the pores get closed as the compact is being forged. So let's say this is the initial pore having this kind of spherical morphology, and as the compact is forged and it is pressed along this axis, then the pores will take up shapes like this. They kind of become elongated, which is known as the shear closure because of the higher shear that the forging operation provides. And as a result of that, they'll be closed in this manner compared to the heaping process, where the pore closure or the shrinking of the pore happens in a uniform manner, as you could see from here. Okay. The densification in the powder forging process relates to the strain epsilon through this particular equation, where nu is the Poisson's ratio and rho is the density. The density and the Poisson's ratio are both functions of the radial strain. Lubrication has a significant effect in the powder forging process because without the lubricant, the forged powder shows low density because of the frictional drag that the punch and the die wall provide on the compact when it is being pressed, and that in turn limits the densification, right? So therefore, if it is not lubricated, a lower density is obtained in the forged compact. And the friction can also cause circumferential tensile forces, and that may even lead to cracking of the compact. It can be visualized from a diagram like this. So let's say this is the initial compact. Having a cylindrical geometry like this. And this is being forged for consolidation to densify it. So when it is forged under compression inside a die, then along the circumference, the tensile stress will be maximum. And this may lead to cracking if there are drag due to friction. Therefore, lubrication plays an important part in powder forging. Okay, so these were some of the processes used for full density processing. Okay, so before we wind up this class, let us take a moment to summarize it. So to summarize today's class, we have started from this looking at the hot consolidation mechanisms again through a diagram like this, and we have seen when the applied stress is high, the densification occurs by the plastic flow when the applied stress exceeds the yield strength of the material. Otherwise, when the stresses are on the lower side, it's a combination of the diffusional flow and the applied stress, which leads to a creep type of densification process. Okay, and the diffusion which occurs can be through either the lattice or through the grain boundary. Okay, so depending on that, a particular mechanism of creep will be operative during the densification process. So in this class, we primarily talked about the different methods of hot consolidation for achieving full density. We started with this hot pressing, and we have talked about this uniaxial hot pressing operation, which is very similar to the uniaxial die pressing that we have talked about before, but in this case, heat is also applied simultaneously for better densification when the powder is being pressed in the die. Then we talked about hot isostatic pressing also, which is the counterpart of cold isostatic pressing in case of the hot consolidation processes. So here the only difference with the cold isostatic pressing is the application of heat, and in order to accommodate that heating, a container which is made of a material which can sustain high temperature is used, and the pressurization can be done by a gas pressure using argon or nitrogen. And in another approach, the pressure can also be applied by volatilization of a liquid, which leads to a higher pressurization rate, and the densification in that case occurs by plastic flow instead of creep. Then we talked about the Hepping cycle also as to how the pressure and the temperature are applied during the process. And finally, we talked about this powder forging process, which is to subject a powder compact which is already preformed to the forging operation. And here, the densification can be achieved in a single strike of the forging die. And we have seen that the pore closure which happens in this case is quite different from the heaping process. In the heaping process, it is basically a uniform closure of the pore because the pressure is applied uniformly, and here you can see the pressure is applied along a particular axis, and therefore the pore is subjected to more shear, and the pore closure therefore is quite different from the heaping process, which exhibits uniform shrinkage, as you could see from this picture over here. And with that, we come to the end of this class, but I'll see you soon again with the next set of lectures. Thank you for your attention.